All right, so section 4.3, complete graphs, simple graphs, and then we'll look at isomorphic and subgraphs. So just kind of starting off, actually we're not going to look at subgraphs in this show, just isomorphic. So looking at the scenario, what we want to do is this is kind of like the scenario they present us. So we have 4 executives that meet for lunch. Each of the 4 must shake hands with each other, and so can we represent that geometrically? So can we represent with an image? So here's person number 1. So we lined up the 4 people in just a way that we can kind of represent it. So here's person number 1. They shake with person number 2. Person number 1 also shakes hands with person number 3. And then we have person number 4 down here. And so now we have representing like 1 shakes hands with all 3. Then we can go to person 2. So person 2 shakes hands with 1, person 2 shakes hands with 3, and person 2 shakes hands with 4. And then we go to 4. So 4 can shake with 2, 4 can shake with 1, and 4 can shake with 3. And then last but not least, we have person 3. So 3 can go with 1, 3 can go with 2, and 3 can go with 3. And so check, that does work. They can shake hands with all people. So let's say we had 5 students and they were going to rent a single 2-seated bicycle, but because of limited time, you wanted to make sure that each student gets exactly 1 ride with each other student. So once again, so we'll start off and we'll call this student 1. So student 1 rides with student 2, student 1 rides with student 3, student 1 rides with student 4, and student 1 rides with student 5. And so we can kind of see that relationship, and you can kind of see at this point, you don't need me to walk you through, but you can see that if we went to 2, then 2 could go with 1 and 5 and 4 and 3 because those paths are laid out. And you could continue on that, looking now at 3 and say 3 can go with everybody because of the paths in between. And so it is possible for us to have these scenarios. So now what does that mean? What are we looking at here? So how are we going to define this? And so we're going to look at the first one is a simple graph. And so a simple graph is in which each pair of vertices is connected by at most 1 edge, no parallel edges, in which we have no edge incident with a single vertex, so no loops. So we have basically 2 requirements. So what this slide's going to do for us is help us visualize what it means to be simple. So right here we have parallel. So this is not going to be called a simple graph because parallel means that we could go from here to here. We could go from A to B this way, and we could go from A to B this way. So we have parallel edges, so therefore that's a not. That one is not a simple. This would be a simple because of the idea that I go from vertex to vertex with 1 edge, at most 1 edge. There's no loops and there's no parallels. All right. Figure B would be a yes also, and that's because I can go from vertice to vertice with 1 edge with no loops and no parallelism. And on the last one, we're going to have a no. And that's because we add on the loop. So loop is what makes this one a no. So simple graphs are graphs that have 1 path between vertices. Complete graphs. So a complete graph is a graph with n vertices in which there is exactly 1 edge incident with each pair of vertices. And so we denote this by k sub n. So in this case right here, we have 1 point or 1 vertex, so it's a k1. This would be a k2 because it has 2 vertices. So n is equal to 2, and so we have, that's the number of vertices, so it's called a k2. Here we have 3 vertices, so it's called a k3. 4 vertices, k4. 5 vertices, so this would be called a k5. Those are complete graphs. All right, so we'll go ahead and touch on this, and then we'll look at the application. So a function so this is actually from section 2, but so maybe you've brought this information from a previous class. We teach one-to-one and onto in a previous class, and so that's why we didn't review it because of time in an 8-week course. So this is a quick review of one-to-one and onto. A function is said a function from A to B, so this would be considered to be A. This would be my A, and this would be my B. A function from A to B is called one-to-one if it does not send 2 distinct inputs to the same output. So for example, 1 is my input, B is my output over here. And so 1 goes to 2. I'm not really looking for like a function pattern, but the whole idea is that 1 goes to one specific number. So that's 1 to 1. 2 goes to 3. That's 1 to 1. 3 goes to 5. That's 1 to 1. All right, so this would be considered a 1-to-1 function versus when we talk about an onto function. So this would be A and this would be B. And so this would be my input and this would be my output. And so in this particular case, a function is onto if every element of B is an output from some element of A. So in this case here, we don't care that they all come from the same X or they all come from the same A value here. We don't care about that. All we care about is that 1 has somebody to go to, 2 has someone to go to, and 3 has someone to go to. And so as long as everybody's coming from something, that means it's an onto function. All right, so awesome.